Hey, Jim Gavigan, Industrial Insight here. We're continuing the conversation with Paul Sheremeto about data quality and what does it actually do to you if you don't get it right. So this segment, this is segment 2, and I'll link segment 1 either in a comment below in the video description, depending on which platform you're watching this. So just look below and you can go back and see what we talked about in the first segment. But really this segment, we want to talk about, well, how do you get it right? And Paul, you've spent a tremendous amount of time trying to figure out how to scientifically, not by feel, not by think, how to get it right. So why don't you walk us through that?
Certainly from a data analytics perspective, it all comes down to recreating what is a good quality of information, and we call that data fidelity. We use data fidelity as a measure within CompressionInsight, and what it gives us the ability to evaluate the signals that would have been archived versus what we call the raw snapshots. And so we create these raw snapshots. So actually in CompressionInsight, we wind up setting exception to 0. So we are turning compression off at the interface so that we're collecting what we call raw snapshots. It's a great starting point for us because it represents 100% data fidelity. We can't get any better than that. And what we then do is, using those raw snapshots, we actually begin to measure the amount of information that is being stored in the archive. We use a part of the background of pattern discovery are all around information theory. Information theory tells us that we can actually measure the amount of information in data. And so what we do is we use these raw snapshots, we recreate the archived values from the configured exception and compression settings, and then we measure that amount of data that's going to the archive. So that's how we get, that's how we understand whether in fact we have a good balance between the data fidelity and the amount of data that's being stored in the archive itself. And so when you think about the challenges associated with setting and compression and exception, is that there isn't a feedback loop for whether it be a process engineer who's trying to set these things or a PI system administrator who's trying to set compression. There really isn't a feedback loop without this ability to measure the actual information in the data. And what we're providing in CompressionInsight now is not only a quantitative measure of this, but we're also being able to show graphically what this information measure looks like, and what the archive information would, or what the archive data would actually look like as well.
Actually, there is a little bit of a feedback there. You know what happens is the PI admin tunes the tag, and the process engineer goes and looks in process book and says, yep, it's squiggly enough now, I believe it. Right? That's the feedback loop.
Yeah.
You know, and like you said, it's almost a little bit more of a black art. Does it really represent the signal? Well, the process engineer says, yeah, looks good enough to me. Right? So that was the feedback loop before.
Yeah, exactly. And so what we're doing is removing that black art and replacing it with a more scientific approach that's based on the data that we actually observe coming from the interface. And then we then set the appropriate configurations for exception and compression that will maximize the amount of fidelity that we're getting that's going into the archive, but taking into account the amount of data volume that we're actually processing at the same time. And so what we set about to do was to create a recommendation that increases the amount of data fidelity, but keeping in mind the fact that we still have to consider the data volumes in order to be able to get the kind of performance that we need out of downstream analysis applications. This new optimization engine that we've created for version 3.0 will will take into account what we call the fidelity ratio, which is the difference between our recommendation and the raw snapshots, and the archive ratio, which would have been the difference between where the amount of data that we're going to store in the archive versus what is comparing to the raw snapshots. And we created an objective function in the algorithm that balances that in what we call creation of this sweet spot. So, and that's all done automatically within CompressionInsight.
So that sounds great, Paul, but what does that really save? I mean, if in theory, that looks, wonderful to me, right? Because as someone who charges customers to do this, potentially do this kind of work, or you think about, any of our joint customers or even customers that aren't ours, but they're yours or neither of ours. What does that really mean for us?
This is actually output from CompressionInsight. These are tags that we would have considered undercompressed. In other words, if you look at the orange graph here, you can see that this is the archive fidelity that we were getting from the original signals. So in this particular case, and in the table at the top shows that what we were getting was 100% data fidelity, or the orange graphs or the orange columns are the archive, and then the blue right beside it to the left of each of those is the amount of data volume that we're actually storing, because we're storing 100% data fidelity. We still have some compression going on, and there are still some information that does get compressed through, because even setting things to 0, you're actually compressing totally redundant data points as well. So we're looking for that balance between data fidelity and the amount of data that we're storing. And so the yellow graphs represent the recommendation that we're making in terms of, now here we're actually reducing data fidelity because we can't improve on data fidelity that it's already we're receiving 100%. So we actually decrease it slightly. So the 3 tags that you see here, they're 97%, 96%, and 93% data fidelity. But what is really dramatic is the amount of data volume, again, because we're balancing the data volume or data storage with this data fidelity. The gray bars or the gray columns represent the difference between or the amount of data that we're actually storing now. So with a very minimal impact on data fidelity, we have a very significant impact on the data that's actually being stored.
So what you're saying here is basically I can store a whole lot less data, but still retain 95-ish% of the actual fidelity, like what the signal looked like, by using your tool. Is that what you're saying?
Exactly. On the other side, so, we have a different problem. On the other side, again, the same orange columns represent a representation of the data fidelity that would have been archived if the original compression and exception settings had been were used. And you can see the first tag there is about 45% data fidelity. Some of the others range between 20, so it ranges between 23 and 70. So the data fidelity is low, which also means that we're not storing very much data. However, what we're very interested now is improving the data fidelity for each of these. And so again, the yellow bars or the yellow columns represent what the recommended, what the fidelity at our recommended exception and compression settings. So you can see that we've improved data fidelity across the board for all of these overcompressed tags. But have a look at the gray column now. We are still, we're storing more data than the original archive settings, but we've achieved this balance where we're only storing in some cases FRC002 there, we're only storing 14% of the total snapshot values and we are still able to achieve 96% data fidelity. So those are very significant in terms of recreating the actual quality of signal that we're seeing in the first place, but doing it with as minimal storage as possible. That's what CompressionInsight is all about.
Well, and I think what's good is, as a user who used CompressionInsight 2.0, right?
Yeah.
Is this part, we could usually get automatically, right? Or is the joking term, I could do automatically, except your stuff actually works, so I could say automatically, right?
Yeah.
It was the other side, that last slide that you showed, where we had to do all that manually. And so now really what the intent, what you have built is you're trying to give the customer out of the box, hey, promote these tags for tuning. And you're going to give them pretty solid recommendations. And we're going to see it in the demo. There's going to be times where you still have to manually kind of go look at things. But the reality is, in more cases than not, you're going to be able to automatically give them something that is probably better than what they're doing now, is what you're saying.
Absolutely. Yep.
That's a pretty awesome premise there.
So in this particular case, this tag FIQ35, you can see the top view is very similar to what we showed earlier in terms of what an archive, if we were over compressing tags. So the red line represents that recreated archive value. The black line that you see is actually the raw snapshots. And so we talked about that earlier. The recommendation that we're making, and the reason that I have this in two graphs, is that I actually have the recommendation turned on in that upper graph as well. The only difference is that you can't see it because it follows along the raw snapshots as closely as it does. And so what I did in the bottom graph here is I turned off the raw snapshots and only exposed the archive values and the recommendations. And you can see that there is very little difference between the recommendation and the raw snapshot value, which means that we're collecting, in essence, 97, I think in this particular case, it was 97% of the raw snapshots. This was FIQ35. The middle graph here is the one that represents. And so you can see, we've done an excellent job of improving the data fidelity. Obviously, that's what the recommendation graph shows in comparison to the snapshot values. But we are collecting more data, but we have a far better quality of information going to the archive than we did before.
In this 20-minute window here, you're collecting 21,600 different sensor readings, right? That's how many have come in this 20-minute window. You're only storing 94 of them, okay? And in that top graph, you're saying, I can recreate that original signal from those 21,600 with only 4,811. So for about a quarter of the amount of data storage, a little bit less than a quarter, then I can recreate that. And then as you show in the bottom of just a few minutes or a few seconds later, you're down to 4787 over that same time window. And I bet if the snapshots were on, it was still in that 21.6 range.
It would be.
But literally that that would be the case. Now the other side of it, if you're on I'm basically not compressing it very much at all, is what you would see is the red line, the black line, and the green line would look very, very similar. Okay?
Yes.
Except the red line and the black line would both be created by, let's just say the red would be like 17,000 points, and the snapshot would be 21,600 points, and the recommended would be 4,811. right?
Right.
It becomes something along those lines, right? So
Yeah.
either side of the coin you're looking at, you're basically saying, hey, if you're storing too little data, I can recommend how you should store a little bit more data, but not nearly as much as turning everything off. Okay. And if you have turned everything off, I can show you how to recreate the original signal, but store a whole lot less data and not let you lose any real information there. Right? Did I sum that up right?
That's exactly it. That's a great summary for sure.